So today we're very happy to have Professor Svi Bern here for our colloquium today. Professor Svi, he graduated from MIT and then did his or undergrad and did his PhD in UC Berkeley under Martin Halperin. And now he's a professor at UCLA. He won the Outstanding Young Investigation Award as well as Sloan Fellow. And in 2014, which is this year, he just received the Sakura Prize for breathtaking contributions path-breaking contributions to the calculation of perturbative scattering amplitude, which led to deeper understanding of quantum field theory and powerful new tools for computing QCD processes. But of course, as with all good physicists, their accomplishment goes beyond what's noted in their prize. He's also known for exact solutions for n equals 4 super EMU, and as well as ultraviolet divergence and supergravity, which is what we will be talking about today. And also, as with good physicists, he knows how to bet. So either money or wine, which I'm sure he'll talk about today. So let's give him a warm welcome.
Thanks a lot for that very nice introduction. I have to say I liked the way you cited the prize much better than the way they did. But anyway, okay, so I'm going to talk about harmony of scattering amplitude from collider physics to supergravity. So in the past decade, there's been really fantastic developments in scattering amplitudes. And I'll just give you a little taste of it. So I'll be a little bit on collider physics, explain some of the progress that's been made in the past decade or so. And then mostly I'll be talking about some interesting structures in quantum field theory and gauge theories, and also supergravity, applications to supergravity, specifically the ultraviolet properties. So scattering amplitudes, they're of course fundamental to our ability to unravel the microscopic laws of nature, specifically at the LHC. So the smooth running of the Large Hadron Collider, it really emphasizes the importance of scattering amplitudes. And this is really a vast subject. And here I'm only going to talk about a little piece of it, leaving out many interesting things, especially in supersymmetric gauge theories. So the first thing I'm going to do is tell you a little bit about Feynman diagrams and the way they obscure structures that help us understand the theories. And then I'll show you just a little bit about modern ways of thinking about the problem. These are called on-shell methods, and I'll explain what that's about. And then, of course, if you have some formalism, some idea, some beautiful structure, then, of course, you'd like to do something with it. So the applications, and really applications are, of course, crucial for any subject, that you have to do something useful with formalism. And so the applications I'll talk about is for LHC physics, how it's used to really do some state-of-the-art calculations of jet production and association with W's or Z's and other particles, tops, and so on. But the main part of the talk is going to be about re-examining the compatibility of quantum mechanics and general relativity, at least the point that people make why it's incompatible. Okay, so every graduate student in particle physics, they learn about Feynman diagrams. And the diagrams, they offer something very important. First, there's pictures, so there's pictorial representations, so you can understand the general structure of the way particles scatter. But more importantly, it gives you, I think this thing is, oh, there. This thing needs something. Okay, now it's okay. So, maybe not. Okay, so the Feynman diagrams there give you very specific rules for doing calculations. So there's no sloppiness in the rules. A very precise set of rules. You see pictures. The pictures mean algebra, and the algebra then represents scattering amplitude. And we'll be talking about just a little bit about there's a tree level. So this would be a typical tree level diagram that you might need to consider for thinking about scattering processes at the Large Hadron Collider at CERN. And this would be the next to leading order. So this is up by power of h bar. So this would be a quantum correction. Okay, and in principle, the Feynman diagrams, they give us a complete solution to this problem. But very, very systematic. Now, there's associated with the Feynman diagrams, there's a large number of issues that you have to take care of, especially in a theory like quantum chromodynamics, theory of strong interactions. It's a problem with many scales. There's large logarithms. There's infrared issues. Then there's non-perturbative contributions. Even questions about the physical states are not so simple, and so on and so forth. All those questions you could have colloquia about any little piece of this. The part I'm going to focus on is, in a sense, very simple and practical. It's given the Feynman diagrams. How do you deal with those? I'll show you that it's not so trivial. Now, back in 1948, Schwinger computed the anomalous magnetic moment of the electron. Here's the Feynman diagram. Of course, Schwinger would not be using Feynman diagrams, but anyway, I draw it there. And then when you look what you could do with Feynman diagrams, let's say around 2010, like around now actually, the answer is we could do 2 more legs than Schwinger could do. And you go, that's kind of weird. We have big computers, very big computers. We've thought about the problem for a very long time, many, many decades. Shouldn't we be 100 times as far as Schwinger went? Well, there is a simple problem with this. And let's have a look. So let's just look at a very simple example. So this would be the next simplest problem which you could give a graduate student in a class on quantum field theory. So that would be a 5 gluon amplitude. The gluons are the force carriers of strong interactions of QCD. So if you're interested in some 2 to 3 process, simplest would be 2 to 2, then you'd have to calculate these diagrams. And that would be a process, you take 2 protons into, it's called 3 jets. It's the sprays of particles that come out. Each one of these lines would turn into jets. So if you wanted to compute this is what you need to do. And you can anybody can do this with a modern computer. You take out Mathematica or some other program, and anyway, it's just a little piece of it. It's about a 25th of it. And if you took out a microscope, you'd see that these are, in this formula, there's dot products and momenta and polarizations. And so basically you get some mass and you don't understand anything. There's no structure. There's no harmony, like in my title. Where's the harmony? Here's a little harmony. Suppose you now use the physical states. This is actually a recurring theme that you want to use quantities that are physical. So you use helicity states. That's the circular polarization. So photons have 2 polarizations. Same with gluons. You use those physical states, and then you use a formalism. These are spinor inner products, but it's really just like circular polarization. It's a fancy way of doing it. It's called spinor helicity, sometimes called Chinese magic, because it is kind of magical. The information you see on here is exactly equivalent to the previous. Right? There's no difference in the information content. It's just that here we've done it in a much better way in terms of physical quantities, very directly. Okay. Now, when you go to loops, that's when the fun really starts. Because at tree level, computers do solve the problem. So suppose you didn't have good ways of doing it, and you're doing very messy calculations. At the end, if you're a practical phenomenologist, an experimenter, all you care about is getting a number. Maybe you're not so interested in this. But when you get to loops, then the problems really start multiplying. And that's because you encounter a few little integrals. Like here is a very simple integral this is for a box diagram, a 4-point diagram. It's 4 Feynman propagators. They're just one type of integral that I wrote down. Normally you have thousands of such integrals, but it's just one type of integral. And there's ways of doing this that were worked out in the 70s, something called Passerino-Vilpin reduction. You feed it through the machinery, and here's what you get. And in fact, this is the answer. If you're wondering what this is, there's some coefficient in front of an integral that's known, a simpler integral. The simpler integral is right at the end there, right there. There's a simpler integral right there. And then there's a coefficient. There's a coefficient that's very complicated. And then to make matters worse, if you look at the actual expression, you'll find it has spurious singularities. A spurious singularity is a pole. It's an analytic pole in the scattering amplitude that disappears. It cancels against other ones. But the problem is if your expression has these unphysical singularities that are supposed to cancel, you lose precision, and basically your life becomes miserable because then it's very hard to compute it. So it becomes actually a real problem. And this, in fact, is the reason why we're 2 legs, 3 legs beyond Schwinger with Feynman diagrams. Things just get out of control very quickly. And it doesn't really matter how big your computer is. That's not going to help you. Okay. So just for a little entertainment, just to give you a feel for what it's like, suppose you said the following words: I'm not going to shave until I finish calculating. Then, if you're a graduate student, your advisor were to assign a W+1 jet production. So that would be a slightly simpler case than this one here. This one is it's got 3 jets on it. But, so then you sit down and you do your work, and your beard grows, and okay, no problem, you look pretty good. If you were to go to W+2 jets, that's already state of the art. People would write entire theses on this. So a few years of work, and you'd look like Hagrid there. W+3 jets, well, it's never been done, so it'll keep on going, at least not by Feynman diagrams. Now, what's the source of the problem? Where does the origin of the problem, or one of the key problems come from? Now, I certainly learned very early on that you're supposed to do things in terms of physical quantities, not unphysical quantities. And when you work in terms of unphysical quantities, generally there's some kind of trouble that happens. Very large expressions or instabilities or some other problem. And of course that happens because you're working with things that aren't physical. Now the Feynman diagrams, they inherently have this problem of not being individually, the diagrams are not physical. And you can see this, it built right into the Feynman rules. There's an integral over all momenta and energies. But Einstein's relation, this would be an on-shell condition if this is equal. Einstein relation says E squared minus P squared is equal to M squared. But if you integrate over all energy and momentum, obviously you violate that. So that means this is not physical. And you could say it another way, it's also not gauge invariant. An individual diagram is not a gauge invariant quantity. The only thing that's gauge invariant is you add it all up, and then you have to put all the particles on shell, and then you get something gauge invariant. So you want to use a formalism, a way of doing it, so that everything is completely gauge invariant. There's no gauge choices involved, and also you want everything to satisfy Einstein's relation throughout your calculation, even in these intermediate legs. You want a formalism like that. Now, if you start thinking about this, luckily we didn't think about this in the beginning, because had we thought about the following issue, we would have probably said it's impossible, you can't do this. But if you look at the reason why Feynman diagrams have this property, that they violate Einstein's condition. You have to integrate over all energy and momenta. You can trace it back to the Heisenberg uncertainty principle. Delta E delta T greater than h bar over 2. And there's a violation of, say, of energy conservation if you're allowed to create particles for a short enough time if you destroy them quickly enough. And that's built into the Feynman formulas. Now, okay, we can do it we like with Feynman diagrams, but you can't violate Heisenberg's uncertainty principle. Right? So it sounds like you need this off-shelliness. You need this integral. Right? You need this in order to get correct results. So you can make a theorem, and the theorem would be based on the Heisenberg uncertainty principle that off-shelliness or energy conservation violation, it's essential for getting the correct answer because of the uncertainty relation. Ah, I see. I get a choice. I like this one. Okay. So it looks like a non-shell formalism of the type I'm talking about. It'll fail to capture everything. Something is going to be wrong. Now, I have a stronger theorem. This is my favorite theorem. It says, theorems in physics are bound to be misleading or have major loopholes. So if you see a theorem, right, in physics, you know there's going to be a loophole. It's just a matter of time before someone finds it. And there's a very simple loophole. The loophole is, what we want to do is we want to get the complete answer using only on-shell data, only on-shell physical information. But that's not the same as saying that in the final result, you want everything to be on-shell. So in fact, the way you get Heisenberg happy is you construct a formalism that only on-shell data is used in the intermediate steps, and then right at the end, you put back exactly the Feynman integral. That's how you avoid it. And that formalism that does on it, we call that modern unitarity method. So unitarity was used a lot in the 1960s. This definitely has a lot of elements from those ideas. But the main difference, it gives us a very systematic way of doing anything for building complete amplitudes from other amplitudes. So you're building loop amplitudes, that's with a loop, putting these legs on shell, and then there's generalized ideas how to do that. And the basic point is this reproduces the Feynman diagram results. It has to reproduce Feynman diagrams or it would be wrong. Right? Because of course the Feynman diagrams are correct, except in all the intermediate steps of the calculation, it's only physical quantities. That's a secret of how this works and allows us to go very far. Oops. Okay, so here's, in regards to QCD. So this is, I stole this from one of the speakers at ICHA in 2010. I was talking about the NLO revolution. That's the next to leading order QCD. That's one higher, that's the loop level. And it's actually a very nice slide, so I stole it. So what this shows is progress over the years, a 2-to-1 process. That was done in 1980. And then a decade later, it's 2-to-2, and then another 10 years, like 2-to-3, another decade, we're 2-to-4. Okay, so, and then there's going to be some list of things that have been done. So now you say, okay, that's very nice. Where's your revolution? It still took 10 years. This is using the modern methods, unitarity. It's still 10 years. Where's your revolution? Okay, here's your revolution. See, to go to the next level, 2-to-5, just another year, and it just continues, 2-to-6. Right? It really works. And it's just a flood of stuff, and you see how the unitarity method just completely dominates now the way that things are done. So it really is a revolution. It really works. Let me just show you a couple examples. Oops. Yeah. Okay, so actually I've been involved in pushing on this. This is something we call BlackHat. If you can ask me why it's BlackHat, it's because we wanted a nice name. That's the real reason. Anyway, that's a C++ implementation of the on-shell methods, and we assembled a very nice team of young people with my collaborators, Lance Dixon, David Kossow, and then some really strong young people to really push this through. It involves many things. There's the algorithms that you need, the specific way that you're going to apply the unitarity, so you can say the physics side of that. Then you have to, of course, write a computer program that implements the algorithm. And then finally, you have to do phenomenology at the end. There's really a lot of pieces in this. The way what BlackHat does is it takes on-shell tree amplitudes and it turns them into loop amplitudes. And the output is numerical on-shell loop amplitudes that then gets fed to, we use Sherpa, it gets fed to another program that assembles the cross-sections, combines it with other pieces and so on. And in fact, it's pretty popular now. There's lots of different programs that use some version of these ideas. Oh, and here's the best part. Atlas and CMS, of course, use that. In fact, one of my friends on CMS recently told me that you can't get a published paper in Atlas or CMS unless you compare it to next to leading order, which is really an amusing change. Not what I was expecting, but anyway, it's very nice. But okay, I don't want to go into exactly what all this is about, but there's a cross-section here, and then the number of jets, and it goes out to very high numbers of jets, many orders of magnitude differences. So it's a very large dynamical range in comparing theory and experiment. And basic thing is it works. It's amazing. So one difference between the next to leading order programs and other programs, they're called part-time starring programs, is that we don't have any knobs to turn. It's fundamental. The fundamental theory is used directly to compare against the experiment. And there's all sorts of corrections you have to do, but the calculation is a clean calculation. If two different groups do the same calculation, you get the same answer. So, oh, I don't know. Oh, what do you mean by too good?
No,
what? Here, yeah. Beats the hell out of me. We got lucky. I mean, it's actually, one thing is, notice it's not that many data points. So
what I mean is that may have to be working too hard.
yeah, that's true. I say nothing about what the error bars on the experimental side are. Yeah, it's actually pretty amazing. And here's, so this has also been compared against data, but I don't have a plot to that here. So this is a really unbelievable calculation in terms of what people would have thought is possible. So this is W plus 5 jet, so it's really very, very complicated. But anyway, the technology works, the programs work, and it's used by these types of predictions are used by experimental colleagues. So it's really good fun once in a while to do something that actually means something to the real world. Okay. Now the rest of the talk will be more theoretical topics. So I'm going to talk about harmony in scattering amplitudes. So you saw a little taste of that. There's a very complicated formula collapse when we use helicity. Now I want to show you something about gravity. That's actually very surprising. Gravity is built from Einstein and Hilbert Lagrangian. Okay, exactly what the Lagrangian is, you have to go to graduate school to know exactly what that means. But in perturbation theory, we can think of it as a generating function for Feynman diagrams. What you do is you take, it's called the metric, and you expand it around flat space, and the fluctuations are the graviton field. And when you plug this in there and expand it, like Mathematica expand, then you're going to find infinite number of contributions. It'll be very complicated, drawn in terms of 3 graviton, 4 graviton, 5 graviton, infinite number of them. Now, when you compare that to gauge theory, so gauge theory is what QCD, quantum chromodynamics, is built on, then you'll see that these things look very different. There doesn't seem to be any simple relation between them. And on top of it, this theory, the theory of gravity, looks to be incredibly complicated. This theory is pretty complicated as well, but that one looks pretty hopeless. Now, it certainly doesn't look harmonious. And in fact, when you look at the details, it looks even less harmonious. So let's have a look at what the 3 graviton vertex looks like. It's actually good fun. So here's the 3 gluon vertex. It's not so bad. It fits on a line. It's a little bit of algebra there. The 3 graviton vertex, I have to use some notation to kind of compress it, make it a little simpler. So there's what's with this one? Okay. So I had used some notation where there's like a symmetrization of these indices, and then there's a P6 which says permutation over 6 terms, so about 100 terms there. And if you show this to a graduate student, especially a clever one, and you suggest a problem based on this vertex, if they're clever, they'll say, okay, that's very nice, but I want to work on a different problem. This is not happy. This is not happy. So where's the harmony? Well, the problem basically is that this isn't some specific gauge. This is not a physical quantity. So there's garbage in there. And the garbage is, in fact, enormous. If you use Einstein's relation, k squared equals 0, you put everything on shell, you impose all the on-shell physical state constraints, then, in fact, the vertex completely collapses. In the Yang-Mills case, well, Yang-Mills was gauge theory. In the gauge theory case, nothing much happens because it's already not too complicated. But the gravity one completely collapses. And it also has a funny structure that it looks just like 2 copies. You see 2 copies of this kinematic factor. This is called the color factor. That's a group theory factor. It looks like it's the square of the Yang-Mills. I'm going to have a lot more to say about that. But anyway, now you see the harmony. Right? These 2 theories, that from the point of view of the Lagrangian, they don't look at all like each other. But at the end, you see there's a relationship between them. Oh yes, that reminds me, I had a incorrect slide, which I'm going to correct. In fact, the modern formalisms that we use today, what they do is they allow us to just directly build from this 3 vertex, just using the simple 3 vertex. The simple 3 vertex here. They allow us to actually build the complete scattering amplitude just using on-shell quantities. Now, that's not something I'm going to really talk about here. But in fact, you can see this very nice relationship between the 2 theories, right? So if we go back here, here, and we look at this theory, oops, there's a little slowness here. I need a new laptop. So if you look here, this theory looks so much more complicated than that. There's no simple relationship. If we look in the on-shell way, you see a very simple relationship. And instead of gravity being a mess, in fact, the conclusion will be, which I'll explain more about, is that gravity is actually not much more complicated than doing gauge theory. And in fact, that'll be the key of how we're going to be looking at extremely high loop orders, these on-shell ideas. Now, here's another example of harmony that is actually crucial to our understanding of gravity. So it turns out that if you want to understand scattering of gravitons, how gravitons interact, you first have to understand in a better way